An important skill for engineers and computer scientists alike is the ability to be able to write a function in a method that a computer or machine can analyze. And one of the things that we do with those functions once we have them, often in engineering, is to be able to do root finding. And in this video, we're going to start a discussion of some of the bracketing methods for just doing that. So without further ado, let's get started. The root of a function, as we defined it back in our algebra classes, was the ability to solve for values of a variable, which we'll say is x, such that the function itself evaluates to a value of 0. One of the earliest equations that you guys learned back in algebra was the quadratic equation, which was used for solving functions that were quadratic in nature. Say f of x is equal to ax squared plus bx plus c equal to 0. If your equation had that form, then we knew the quadratic equation was that x was equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2 times a, where a, b, and c are the coefficients in front of the x squared, x, and constant terms as shown there. Okay. And so this tells you that we have two roots. One is root is created by the positive sign here, and the other is created by the negative sign there. Okay, and if I plug that x value back into here, my function will be equal to 0 or very, very close to 0 in the case of numerical sensitivities. Okay, but what do you do when you don't have a quadratic equation? Anything of higher order or of a trigonomic nature is a little bit more challenging. Okay, and so we need to come up with methodologies or techniques for being able to find those values of x. Okay, these roots have different meanings and different importance in all of our engineering applications. So we've got to come up with a methodology that will allow us to solve something a lot more complex. I mean, say that you have a function in this case that is e to the x minus x. Okay, well, we have a couple of options to be able to do this. Okay, so some of the methods that we can do is we could find the answer analytically, right? I could set this equation equal to 0, and then I could plot e to the x, and then I could plot x, and I could graph those, and wherever they cross, that would be the location where this sum would be equal to 0. That's one way to be able to do it. Okay, the other is we could just do a blind guess and check, right? I could choose a value of x and test it, and then I could choose another value of x, and I could test it as well until I get to a form where that function evaluates close to 0 or approximately 0, or what we would say is close enough. So we want to come up with a way that's a little bit more logical than that, or a methodology that will guarantee that I can find a root in most cases. Okay, but we also need to be aware of some of the pitfalls that can happen along the way. Okay, so here's what we're going to do is we're going to kind of set up our methodology as such. Okay, if we know that one of the roots is between two values, let's call it x lower and x upper, xl and xu on this. Okay, if the function evaluated at xl and the function evaluated at xu have the same sign, then there would be an even number of roots that have to occur. And we can see that by plotting this picture here. So let's just draw an arbitrary function line, say this kind of squiggly line here. And we know that if we know the number of roots, if we know that we have two roots, that occur between my two limits on this, then when this function dips down, it crosses 0, goes negative, then comes back across. There are the two roots. Okay, and so that's one of the things that we would take a look at. Now, if we take a look at if f, because at this location the lower value had a positive value of the function here, and the upper has a positive value of the function here. So in order to go from here down and then come back, I had to go into negative and come back, so that's why I crossed 0 twice. That's how I knew there were two roots. Compare that to, say, a function between the same two limits in which I only cross one time. Okay, that they have opposite signs, so this is a positive and this is a negative, then I have to cross 0. There has to be a root that lives in between there. Now again, there are rules such as the function has to be continuous. We can't have any, it has to be a valid function to be able to be evaluated in this manner, but we can use the signs to help us kind of determine the quantity of the roots. Okay, now, this particular example had 2 roots. It could have just as easily come up and crossed many times, so to say that it was 2 wasn't correct. It was more likely that it was an even number of roots. Okay, in order to be positive and end up positive, I have to cross 0 an even number of times. And you can try that by just plotting some of these and experimenting. Also, for the single case where we said 1 root, it's really better to say that it is an odd number of roots. Okay, because it could come down and then it could go negative, then come back positive, and then go negative again, and that would get me my positive and negative signs. So even and odd is a better way of saying this. There's no way to know the exact number of roots, at the start of this process. Okay, which presents us with a potential problem. Okay. All right, say, are there any problems with this idea? Okay, well, the first problem that we have is that if the numerical roots, what if f prime x, meaning the first derivative of my function, is equal to 0? Well, we know from calculus that this point, if the slope is 0 at my root location, that means that I have either a maximum or a minimum that occurs. And when you draw this is something that we look at like this. So if we take our scenario where we had, say, an odd number of roots, with a positive here and a negative here, if my function comes down and hits 0 at a maximum or minimum on this value, and then turns around and goes back up, well, it never crossed. It hit exactly 0, but I didn't get the down and back situation that we were talking about. And so if it does this, then I have an even number that fell through, even though my signs are opposite. So that's a potential problem. Now, this one's an easy one to catch. All I do is once I have my root value, I can test the function and find out. And if I know that I have it equal to 0 or that it's a maximum minimum at that location, then I can be aware and we can kind of head this one off. Okay, so that's kind of one of the problems. So our statement, if multiple roots can get an even number of roots between opposite signs, or an odd number between the same sign, because of a tangential x-axis at one of the roots. Okay, and so that becomes an issue. So we have to be able to test this, all right? And when this situation happens, the form of this function we know would be x minus whatever this root value is, okay, and then squared, okay, and then x minus, the root value for the second one being multiplied by that, okay? And so what happens is that you get this exponent on here that indicates that it was what we call a repeated root. Okay, or a double root has to occur on this kind of thing. Because you remember, when we found roots were, if I had plus 3 and minus 3 as my roots, remember your function, we would write this as f of x is equal to x minus 3 times x plus 3 would be my equation for that. But if I had, 2 roots of plus 3 on this thing, then I had to put a squared term on there. That's all that's saying. That this is the more general form of writing that equation for repeated root. Okay, so that kind of illustrates that we need to come up with a methodology to deal with multiple roots. Okay, so suppose we have an nth order polynomial that has n roots. Okay, now we say n roots, but not necessarily n distinct roots. Distinct would mean that they were all different values, in which case it's the same methodology that we've been talking about. It's these repeateds that we have to deal with. So for now, we're going to assume that all of our roots are distinct and talk about some of the methods that we can create in order to come up with what are the values of x that solve that equation, all right? And so this is going to lead us to a discussion of something known as bracketing methods. And basically what a bracketing method means is that I have a lower bound and an upper bound limit in which I know that there's a root that lives between those two, okay? And we'll talk about how we can put those to work. There's another category of root finding known as open methods, in which I have one root and a first guess, and then I can go off and try to find it. And there are obviously some problems that come up with that as well. All right, so let's talk about the first method here, is what we call is the bisection method. Okay, is that we're going to start with our x lower and our x upper, okay, such that my roots are the functions at the lower limit and the function at the upper limit all have the opposite sign. Okay, this would ensure that I have an odd number of roots crossing over it. So what we're going to do is we're going to find the midpoint of this bracket. Okay, and we're going to call that term as xr, such that xr is simply the average of those two values, xl plus xu divided by 2. Okay, and when I do this, we have now found the midpoint of this particular function. All right, so what we do is that we then take this number, okay, and we're going to evaluate the function at that point, okay, and one of two possibilities occurs. If the function evaluates at 0, we're going to stop because we found the root. Okay, if the sign of our new point, our midpoint, and the sign of x lower are the same, then we're going to change the x lower value to this new guess. Otherwise, if they're opposite signs, we're going to replace the upper value with this new point, and then we're going to iterate and repeat this process over and over again until we eventually converge on the limit. So here's what we're going to kind of look at. So if we kind of draw this pictorially for a function, okay, let's just suppose that I have a function line that comes in and does something like this. Here's my lower limit, okay, and here's my upper limit. Okay, if we take our first guess, so here we have a positive value, here we have a negative value. If I take my first guess over here, this is my first guess, for this particular function, we would show that it would be a negative point here. What the method says is it says, okay, well, if I know that I have one root between here and here, when I do my bracketing on this, and I choose here, then it means that this point, you know, we're going to cut him off and look here, and now my bracket is this big, right? And so we play the same game again. So here's my first guess, okay, and we've replaced it. Now I go to the next point, and so this would be my second guess, and if you look at it, we're still negative, so this guess now comes up to here, and now we're here, okay, and so we play the same game. We would drop this one and know that my root falls between these. So in two guesses, I know that it's which quarter of the bracket it's located in. Okay, and so I get to here, and then I go through, and so now it's still negative, and then I go and I do it again, and look at my midpoint on this location, and now it's positive, so now I take this point and I replace this point. Okay, so now I have a bracket between here, and each time you're getting closer and closer by a factor of 2 to what the bracket is. And basically you just keep iterating this, and what happens is these 2 points will constantly, they'll squeeze in on each other, and eventually I'll be so tight after doing it so many times, I'll be so close to the root that I know that the root lives between those two values, and I'll have a very small range for it to work with. Okay, and so that's kind of the way that we can kind of work on this. And so we just keep repeating this until, you know, that we either find the root as approximately 0, or more realistically, usually we say that we're within a certain tolerance, you know, an error tolerance. And we talked about this in one of our earlier videos, that we're in a limit, you know, say, you know, 1% or 0.1%, or whatever the limit is that you're comfortable with for knowing that value. Okay, all right. And now here's the thing with this. Very seldom, for most functions, when you evaluate that middle point, very seldom is it exactly 0. Okay, and so what we do in order to be able to look at our approximation error on this is we take the value of our new XR, okay, and then I turn around and compare it to the previous guess of XR, okay, and then divide it by the XR of the new, and now we've got our kind of our relative error, if you will, okay, and so multiplied by 100%. So we start looking for small percent changes. When these two values are very close to having found the root, this difference becomes very, very small. Okay, so if this gets small enough, then you're within a small region of the true root, and that's kind of we can use our approximation error. This is the type of equation that you'll find, you know, in a computer algorithm or some sort of automated process that is used to find root finding. You'll find an equation that looks like this a lot of time. Okay, now the bisection method we know is easy. Okay, but this is what we call the kind of a brute force method. You know that every guess you're closing in by half. Okay, so if you start out really, really far apart, it's going to take you a lot more guesses to narrow the bracket down. So what we want to do is we want to try to come up with a more, what we would say is more elegant solution, or something that's a little bit more, doesn't have some of the pitfalls of what we have, okay? And so what we're going to do is we're going to come up with a method known as the false position method. Okay, now it's very similar to the bisection method, okay, in that we're going to use our lower root value here and our upper root value here to estimate our roots. Okay, now what we do instead of finding the midpoint, because one of the things that you have is we're not taking advantage of the magnitude of these particular points. If this magnitude is really, really small, it means your root is most likely very, very close to XL. Whereas if it's very, very, very big, and imagine this line is coming down this way, then our root is closer to X upper. And so what we do is we say, well, let's take our guess and let's kind of change it a little bit, okay, and that we look at this formula, you know, and basically what we're going to do is we're going to basically plot a straight line between the values of our guesses, and then use some sort of, you know, similar triangle approach to determine where this point is in relation to the size of the height of the values of the function. Okay, and if you kind of look at this, you know, what we have is that the next guess, our root guess, is going to be equal to the x upper minus the value of the x upper times the distance xl minus xu, that's from here to here, okay, and divided by the value of the lower minus the value of the upper when they're evaluated in the function. So kind of hiding in this is the bottom term is it's kind of like saying delta x times delta y, okay, multiplied by then f of xu there. All right, well, if I look at this is kind of the inverse of the slope. Okay, and so then I can say the other side would turn into an xr minus an xu, okay, which would be kind of the distance from here to here, okay, multiplied by the slope times the height of this thing. And if I do that, that's what gets me kind of a proportion. It's kind of a proportional check to be able to locate this. So you're not necessarily in the middle point. Now, if the height is the same as this height, you will be in the middle point. But if it's not, this will skew your guess towards one or the other. Okay, so then what I do is I take my function values and I take the value of xl and multiply it by the value at xr. Okay, basically all we're doing is a sign check, and if that product is less than 0, then we're going to take the guess and we're going to replace xu with that guess. And likewise, if you find out that the sum is positive, then xr is greater than that limit. Okay, we're going to replace the lower bound value. Okay, and as always, if you find out that it's equal to 0, then xr is our root on those. So this is another method known as the false position method, which is kind of an improvement on the bisection method that we talked about just a moment ago. Okay, now there are some problems that occur with the false position method. Okay, so typically, okay, the false position method will converge faster, but not always. Okay, and so suppose that we have a situation where my guesses, so here's my lower bound, here's my upper bound. Okay, and what will happen is that if both of these guys are very, very close to 0, my next guess for x1 would be very, very close to this. Okay, and so it could be very, very, very slow as it moves its way. It's moving towards the root that's located here. Okay, but the false position, because of that ratio of the values on here, that I could be very slow to converge here. That, my first guess will be here, and my next guess will be a little bit closer, but it's still a long ways. It's not moving very fast this way. So this rate of convergence is kind of an issue on this, because the method says take this point, draw a straight line to the upper limit on the other end of the bracket. Okay, and that's how I find, oh, this was my guess. And so now I come down and evaluate this one and do it, I'm here, and so forth and so on. So for very, very flat slopes, where functions are, not necessarily constant, but whether they're flat, it can be very, very slow to move its way towards the actual true root. In this particular case, the bisection method would have been faster, right? Because I would have gone straight to that middle point, and I would have been that first guess would have been closer. So that's one of the pitfalls, is for some of the shorter slopes, if you will. So those are a couple of methodologies that we have for bracketing methods. In the next videos, we'll start talking about open methods or non-bracketing methods, okay, which kind of solve one of these problems, but then in their own right have some other mistakes. So as always, I hope this has made sense to you. We'll check back with some more root finding methods in the upcoming videos. Let us know if there's anything that we can do to help make things a little bit more clear by leaving a comment down below, and then be sure to like and subscribe to our channel for more videos that will be upcoming. So have a great afternoon. We'll see you all next time. Bye.